Welcome back everyone. In this lecture I am going to recall what we have proved in Fourier analysis on finite groups, and then later we will see some application of Fourier analysis in spectral graph theory. So, let us begin by recalling what we have proved. So, let me make it very precise. So, we start with G being a finite group and then assume that the cardinality of G is n and S is given to be the number of conjugacy classes of G. So, let us denote this phi 1 etcetera phi s to be the set of unitary representatives of the equivalence classes of irreducible representations of G. So, I am going to write it as irrep of G, which is listed as phi 1 etcetera phi s. So, we are going to assume that they are all unitary representatives. So, now as before we fix that dk to be the degree of the representation, which is exactly the dimension of the irreducible representation. So, with this notations we also have like these matrix coefficients, let us fix them. So, given k from 1 to s, so we denote this phi I j k. So, these are the matrix coefficients which are functions from G to C corresponding to the matrix of phi g. So, where phi g k is given to be phi I j k of G. So, this is the notation for the matrix coefficients. So, now with this we will define the Fourier transform. Okay. So, let us recall that. So, the Fourier transform is a function from C g to this product of the matrix algebras. So, you take M d 1 C cross etcetera cross M d s C, where given f we associate this tuple f hat of phi 1 etcetera f hat of phi s, where this f hat of phi k is nothing but the summation f of g phi k of g. Okay. So, this is the definition of the kth coordinate endomorphism map. So, like I said, this is indeed living inside M d k C. So, if you do not fix the basis, which you can identify with the endomorphism of that V phi k. Okay. So, this is the map that we are talking. So, I forgot to put this conjugate. So, we just keep that conjugate here. So, in many other books actually they do not use this conjugate, they just simply write it as summation f of g phi of g, but since the duals are available in our category of representations. So, the dual of irreducible is again irreducible. So, that actually would immediately tell us that whether putting this bar, not putting that bar, okay, this bar does not make any big difference. Okay. Still we will have the isomorphism. Okay. So, let us actually go through slowly and then check the properties that we have left. So, recall. So, we have this map T from C g to this matrix algebra M d 1 C cross etcetera M d s C, where f is sent to this f of phi 1 etcetera f hat of phi 1 etcetera f hat of phi s, and where f hat of phi k defined to be summation g in g f of g phi k of g bar. Okay. So, this is what we have defined. Now, what we want to check this is indeed linear map from this vector space CG to the targeted product of matrix algebras. Okay, so why this is linear? So once we prove this linear, Fourier inversion, which we checked, immediately tells you that it is indeed an injective map. So since the dimension matches on the both sides, so the dimension of this is exactly given by the cardinality of G, and dimension here is given by summation di square, but we already know that the sum of di square is exactly equal to n. So that observation tells us that once we prove T is injective, so T is injective would imply immediately T is surjective. Okay. So T is injective plus linear transformation tells us that T is surjective. So T is injective is the Fourier inversion, which we already checked. So only part that we didn't check is the linearity, and linearity will come for free from the fact that this can be identified as the inner product. So which is exactly equal to n times the inner product between f and phi k. Okay, so let us look at carefully how it is actually done. So if I start with F1 and F2 coming from CG, and then C1, C2 comes from C. So let us look at the combination C1 F1 plus C2 F2, and then look at its Fourier transform. So then evaluate at phi k and then see what happens. So this is going to be exactly equal to, so we want to check this is exactly C1 F1 hat of phi k plus C2 F2 hat of phi k. But by definition this is exactly equal to summation G in G C1 F1 plus C2 F2 of G times phi g k. So or phi of g k, maybe I will use that notation, phi k of G bar. So now you can see that this actually can be using linearity. So this can be written as follows: this is C1 F1 of G phi k of G bar, where G runs over G, plus summation G in G C2 F2 of G phi k of G bar. So now C1 can be taken out, then this is exactly C1 F1 hat of phi k, similarly plus C2 F2 hat of phi k. So this tells us that C1 F1 plus C2 F2 hat is same as C1 F1 hat plus C2 F2 hat. So this proves linearity. Now injective follows from Fourier inversion. Now the dimension matches, so that would imply that T is an isomorphism. So we also checked T is indeed isomorphism between the rings. So in particular T becomes isomorphism of algebras. So indeed this T is an isomorphism of algebras, C algebras. So that is actually the statement of the Wedderman theorem. So the Fourier transform is an isomorphism between CG and this product of matrix algebras. So let me just state it for completeness. Wedderman theorem so the Fourier transform from CG to this product of matrix algebras is a C algebra isomorphism. Okay, so that means one will be able to actually recover given function using its interpretation in terms of the basis that consisting of matrix coefficients. So, that is what this theorem actually tells us. Okay, so now we are going to actually see how one can use Fourier analysis from the application point of view. So, as far as basic number theory are concerned, or additive number theory or additive combinatorics concerned, Fourier analysis on finite abelian groups are used very much. But right now what we are going to do, we are going to actually see an application in graph theory. So, let me actually motivate the problem and then slowly build up and then see how one can apply the Fourier analysis in this situation. So, what we want to do is we want to see an application to graph theory. So, let me recall the definition of graphs. So, we assume that all graphs are actually simple graphs. That means it only consisting of vertices and edges. So, no multiple edges or loops are allowed. So, we assume V comma E. So, this is given to be graph. So, this is indeed a simple graph. So, that means no loops and no multiple edges. So, graph consisting of a pair V. So, this we usually identify with the, let us say, finite graph. Okay, everything is finite. So, we identify the vertices by 1 to n, and the edge set is indeed, one can identify it as a subset of V cross V. Okay, since we are only talking about, so maybe like either we can identify with as Ij, or we can actually denote it by more of unordered pairs. Okay. So, let us say E consisting of unordered pair Ij for some Ij's. Okay. So, the graphical interpretation of graph will be better. So, what we mean by graph? So, let us do some examples. So, E consisting of unordered pairs of elements of E. Okay. Some unordered pairs of elements from the, and they are called edges. So, these are called vertices and E are called edges. Okay. For example, we can interpret, we can draw a diagram like the vertices will be denoted as dots on the plane, and then the edges will be represented as line segment between the vertices. For example, if we take this path P4, so then that consisting of 1, 2, 3, 4 vertices, and then we put an edge between these consecutive vertices. So, that means the vertex set is 1, 2, 3, 4, and the edge set is given to be 1, 2, 2, 3 and 3, 4. So, this is the set of edges for path P4. So, now given this graph, so we can actually define the adjacency matrix of that graph. So, the let us say G, okay, let me use gamma for the graph because G denotes the group. So, let us call this gamma to be the graph, and this gamma is P4 here. So, now given gamma, which is the graph, simple finite graph. So, then we define this adjacency matrix, we call it capital A. So, this is the adjacency matrix. So, let us denote Aij to be its ijth entries. So, it is given by this Aij, it is either 1 or 0 depending upon whether there is an edge or not. If ij is an edge, then it is 1, otherwise you call that ijth entry to be 0. So, for example, if we take the path P4, so then the adjacency matrix of P4 is going to be, so you have 1, 2, 3, 4 vertices, 1, 2, 3, 4. So, you know that 1, 2 and then 2, 3, 3, 4 they have edges, remaining things does not have any edges. So, 1, 1 does not have edge, 1, 2 has edge, 1, 3 does not have edge, 1, 4 does not have edge. Similarly, 2, 1 has an edge, 2, 2 does not have, 2, 3 does, 2, 3 has, 2, 4 does not have, 3, 1 does not have, 3, 2 has, 3, 3 does not have, 3, 4 has, 4, 1 does not have, 4, 2 does not have, 4, 1, 4, 3 has, 4, 4 does not have. So, from the definition it is clear that since whenever there is an edge between I and j, there is an edge between j and I, okay, I j in E, if and only if j I is in E, that tells you that the adjacency matrix is always symmetric matrix. So, the observation is that adjacency matrix of G, so that is indeed real symmetric matrix. So, this is real symmetric matrix. So, now if you use the spectral theorem for say real symmetric matrices, that immediately tells that the adjacency matrix is always symmetric and hence diagonalizable with real eigenvalues by the spectral theorem of matrices. So, immediate conclusion is that AG is diagonalizable. Not only it is diagonalizable, its eigenvalues are real. Okay, all eigenvalues of AG, they are indeed real. Okay. So, in practice the adjacency matrix possesses all information about the graph, and if we think about it more, one can obtain many important information about the graph from the eigenvalues of its adjacency matrix. For example, one can actually give explicit formula of the number of spanning trees in terms of the eigenvalues. Also, one can easily verify that, maybe you can take this as exercise. So, if we take this nth power of this matrix AG, the adjacency matrix, and then look at its ijth entry. So, then this exactly counts the number of paths of length n from I to j. So, this exactly counts the number of paths of length n from I to j. Okay. So, path we already know what it is, I am not spending time on that. So, path from one vertex to another vertex, it is a sequence of edges that actually the tail of one edge should be head of another edge and so on. So, if you look at the higher powers of this AG, so it is kind of includes somewhat many interesting combinatorial data about the graph. So, that is what this exercise says. So, that means if you are interested in finding this higher power, so using the diagnosability, so it is important to find the eigenvalues of AG. Okay. So, since AG is diagnosable, so if you are able to find B, which is diagonal matrix whose conjugate is AG, then if you are interested in finding the nth power, then it is clear that, so it is enough to actually find nth power of this B. If B is given to be the diagonal matrix consisting of the eigenvalues of A, then it is clear that computation about AG becomes clear from the computations of B by finding this this conjugation capital P. So, you have this B power n, which is given by lambda 1 power n etcetera lambda n power. So, let us call it K. So, here I guess I have fixed n to be number of vertices. So, we modify this by K. So, number of paths of length K from I to J. Okay. So, the importance of eigenvalues lies in the computations about AG. For example, if you are interested in finding the power of AG or the inverse of AG, it is enough to actually compute theoretically what are all the eigenvalues. Once we know what are all the eigenvalues, so then we can actually conjugate AG by some nice matrix P, so that it becomes diagonal. So, then doing all computations about the diagonal becomes much easier. Using that computation, we can recover all computations about AG. So, that is the talks, that is what diagnosability is used for. So, this tells us that like if you are interested in many combinatorial information about the graph, then we need to look for this spectrum of this adjacency matrix, which is also called the spectrum of the graph. So, the study of this spectrum of the graph is called spectral graph theory, and it is a branch of mathematics that is very much used in many real life applications. So, here now we are going to actually use representation theory to in order to actually understand spectrum of some special graphs. What are they? So, of course, they should be somewhat related to the groups. So, given a group, there are natural sources of graphs that are known as Cayley graphs that actually comes from by fixing some generating set of the group G. Okay. So, let me define what is Cayley graphs. So, Cayley graph of given group G. Actually, to define Cayley graph, we need two data. One is the group, another one is symmetric subset of G. So, let us fix a symmetric subset. S is subset of G is said to be symmetric if it satisfies two conditions, because we want it to be generator. So, we just assume that the identity element is not there. And the second condition, whenever S is in capital S, then we demand that S inverse is also in capital S. Okay. Such sets we call it as symmetric set. Now, given this group G and a symmetric subset of G, one can define the Cayley graph as follows. So, G is given, S is given. So, from this we want to define this Cayley graph. So, what is the vertex set for this Cayley graph? You take the vertex set to be G itself. So, we take the vertex set to be G itself, and then we put an edge between G and H. So, draw an edge connecting G and H if G H inverse belongs to capital S. Okay. So, this is how we actually draw this Cayley graph. You take the vertex set to be entire G and edge set to be those you connect G and H if G H inverse belongs to S. Now, since S is assumed to be symmetric, so that tells us that whenever G H inverse is there in S, that would imply H G inverse is there. Okay. So, G H inverse is in S implies H G inverse is in S. So, that means what we get is actually undirected simple finite graph. So, now we take this graph and then we want to study the spectrum of this graph. So, we can talk about the adjacency matrix of this and then we can also study the spectrum of that adjacency matrix, and we want to kind of get as much information about that spectrum of that adjacency matrix of Cayley graphs. So, let us see some examples. So, if you take S to be empty set, then the Cayley graph will not have any edges. So, then this Cayley graph, so let us denote it by let me use this notation. So, given GS, the Cayley graph we denote it by, let us say, gamma of G comma S. Okay, if we use that notation, then it is clear that gamma of G comma empty. So, this is going to be what is called trivial graph. So, trivial graph means the vertex set is going to be capital G, but edge set is going to be empty. So, that means no edges are there. So, totally disconnected graph actually. And it is an easy exercise to see that this Cayley graph is connected if and only if that set capital S indeed generates capital G. So, maybe we will leave it as exercise. So, gamma GS is connected if and only if S actually generates G. S generates G. So, what is the meaning of connected? That means any two vertices can be connected by a path. So, this means any two vertices of gamma GS is connected by a path, and that would actually tell you that so you can go from one element to another element by keep multiplying by elements of S. So, for example, you can actually connect any element with identity by a path. So, that tells you that any element can be obtained by just multiplying by elements of S. Okay, let me just draw one diagram. So, we can take G to be Z mod 4 Z and then S to be just plus or minus the class 1. So, then if you just look at the Cayley graph of this gamma GS, so then it will look exactly as follows. So, you have 0 and then you have 1 and then you have 3 and then you have, let us say, 2 here. So, now you can see that 0 and 1 are connected. So, there is an edge between 0 and 1 because 1 minus 0 is indeed 1, that is there, and then 1 2 there is an edge, 2 minus 1 is 1 or 1 minus 2 is minus 1, similarly 3 minus 2, and similarly you also have between 0 and 3. So, because minus 1 is same as 3, so 0 minus 3 is exactly minus 3, which is plus 1 modulo 4. and we can't have anything between 0 and 2 and 1 and 3, because 1 minus 3 is minus 2, which is plus 2, which is same as 0 minus 2. So, which is not going to be in this plus or minus 1. Okay. So, that means this is the graph that we are going to get, and whose adjacency matrix is going to look exactly like, it is a 4 by 4 matrix. So, if we just look at it from the graph, it is just 0 1 0 1 and 1 0 1 0 0 1 0 1 and 1 0 1 0. Okay. It is a symmetric matrix with this. So, indeed it is not difficult to see that it is a circular matrix. So, I will define what is circular matrix and then connect it with this. Okay. So, I will stop here. We will actually see how to use representation theory in order to understand the spectrum of these Cayley graphs in the next class. Thanks.